All right, so in today's episode, I wanted to talk about bytes. We have briefly touched on this idea that everything is a sequence of bytes when it comes to data, right? And we can interpret those sequences really however we would like or however we should, and so on. But saying that to someone who doesn't necessarily know what a byte is does not help them, right? So we're going to go over today, it's going to be in some sense a little bit more foundational. If this is something you're completely comfortable with already, feel free to just sort of skip along, right? So we're going to talk about bytes and how they are, well, what they are, how we actually can sort of deal with them, how we can express them, how we can think about them, and so on. Note that I'm not going to be saying that how I describe this or whatever is absolutely the best way to think about any of this stuff. It's more like this is how I personally think about it, and so on. Feel free to give feedback that you have. Either, I think about bytes like this and blah, blah, blah in the comments. I'm sure that will be helpful for a lot of people. So, what is a byte? A byte is 8 bits. A bit is either 1 or 0. The way that these are laid out is basically just a sequence of 8 bits, and these are slots, we can view them as. When a slot is filled in, it has a certain value. So let's take a look briefly here, right? We have this descending scale of value here. So we have 1 and 2 and 4 and 8 and so on. And as it happens, we can describe any number from 0 to 255 with this particular scale here. These are the actual values we can represent if we have these numbers here. So if I were to represent 1, I would just say 1 in this slot here, right? And for 2, likewise, I would say 1 here. So we can illustrate this fairly simply by saying task bits and bobs here, which runs this program. And here we can see how it actually works, right? So you can see here that 1 is traveling across, and the numbers that we have here are corresponding to that value, right? And if we want to express this in Odin, we can simply say, well, 0b, right? And so the reason, by the way, that I have elected here to, there are two things at work here. I have elected to put zeros everywhere. This is just to get a uniform kind of expression for these here, to always use 8 bits here. You don't necessarily need to do this, right? So if we, for example, if we did this, we would see that 1 is not different. 0b1 is exactly the same thing as what we had before, right? So this these leading zeros are not needed, right? But for this example, we want them because they provide this pattern again, the traveling 1, so to speak. So I have also done another thing here. I have sectioned them in 4s, right? So these sections of 4, actually, if I, let's see if I can find. So here you can see that Wikipedia will tell you that a nibble is a 4-bit aggregation, or half of an octet. And when you see people mentioning octets, what they're actually talking about is just this byte, right? Because it's octet, right? An octet of bits, right? So this entire thing here is an octet, and this here is a nibble. So half of a byte, right? These are 2 different sections, and they're usually represented as such. So when we print something in hex, for example, we will actually get 2 different. We will actually be printing the nibbles, you could say, right? So anyway, here we have these numbers here. So if we wanted to actually add together certain things, like let's say we wanted to represent 5, right? So let's say B5, right? That would be 0B, 0, 0, 0, 0, 0, 1, 0, 1, like this, right? The reason, of course, is that this would be 1 and this would be 1. As a small note, whenever you see an odd number, it always has this bit set, right? Because it's 1. All of the other ones, they literally cannot make an odd number. So whenever you're looking for an odd number, a very easy filter is just the binary pattern would be would have 1 at the end, right? So this 5 here, right? If we were to, let's see if we can, let's run this again. We can see here that we get 5, right? And so whenever you're adding these together, personally, I'm not super strong with just doing basic arithmetic really fast. And it's even worse when I'm recording, obviously. But you can essentially, whenever you want to represent a number, just think about sort of what is the largest thing, the largest factor here that I can use, and then go downwards, right? So for example, for the number 5, we know that 4 and 1 make 5, so we could just say immediately, okay, the 4-bit is set, right, and so on. If we wanted to represent, let's say 15, right, we know that, oh, 8 goes in because 16 can't. 8 goes in, right, and then we set number 4, that makes 12. We set number 2 and then we set number 1 because it's odd also, right? But yeah, so binary representation here is a fairly, we want to kind of be comfortable with this idea, right? Not necessarily because we're going to be writing these binary patterns a lot, but we need to be able to deconstruct at least into these nibbles and move between binary and what's known as hexadecimal fairly often. So let's take a look at what that means. Let's see if we can print printf and so hexadecimal is written with 0x, so you can see here h5 0x, let's say x5 rather, like this. And so what we're doing in hexadecimal is actually, I'm gonna just say this. When we have an x5 here, right? First, let's just say that we have the actual number first here. Let's remove this, put in parentheses the actual hex value. Want to, of course, pass x5 twice. Here we could just say this maybe. Yeah. And so here you'll see that it has removed the leading 0. Can I add that back maybe? I don't know how to do that. Regardless, what we actually have here, right? This is hexadecimal notation for the same thing as this. And so what it does is it takes basically it represents the nibbles as in hexadecimal notation. So if we say here, let's see this. actually, that's a. So what we actually get here is this. So these numbers from 0 to 9 are represented by just their numbers. So for example, we have the 5 here. But any value beyond that, up to 16, is represented by a letter. So A, B, C, D, E, and F instead. So for example, it would be valid here to say AF. Right? And that would mean that this upper, these upper bits, right? This upper half of the byte would be set to A, meaning 10, right? So if we were to represent that, let's say XA5, we're going to call this XA5. This means basically BA5 is equal to 0B 1010 0101. And the reason for this is, of course, now we have this grouping, right? And A, right, is 10. So we want to set 8 and 2, right? This makes A 10, right? So 2 plus 8, 10 makes an A, and 0xA5 then is the sequence 1010, and then for second grouping, which is 50101. Right, so you will often see these types of representations, right? So for example, here I can say XA5 instead, and we can see here BA5 declared but not used. Sure, let's just actually let's show that these are the same. Right, so these are the same number. They're just written a different way, right? And we can feel free to write these any which way we want. And you can see here also that the decimal value of this number is 165. So we could also have just DA5, which is decimal, 165, like this, right? And that would be completely valid and completely the same as well. Right, and so when we actually talk about these values sort of on their own as bytes, right, we will often see these two notations come into it. More often than not, it's going to be hexadecimal, especially when we're looking at things that are larger than a byte, right? So that when things are larger than a byte, we tend to instead see groupings of nibbles. Right, so these octets, these 8 bits, right, bytes are going to be represented in hexadecimal, one number or letter per nibble, right? And so we will often see these kinds of pairings that way. So for example, if we were to actually look at a larger number, let's just say, let me find an example. Yeah, okay, hang on. So we can represent the number like this here. By the way, these are all ints by default. I should show that. so that people know this. Just because you have just a 1 byte here does not mean that it's going to actually be this, right? You would have to specify this is a byte and so on. And in fact, you should be able to just fine like this, and it shouldn't be an issue. Here, we can see that we have several of these octets, right? So each of these is a nibble, right? So we have 1 is a nibble, right? 8 is a 1 nibble, and so on. They make up a byte together. This is another byte, and this is another byte here, and then the last byte. So in fact, we have 4 bytes here, right? And if we were to actually print this number as well, right, we would see that it is this number here, in fact, and it has this exact representation that we gave it, right? And it wouldn't matter how I specify this, right? Let's say we changed our source code here to just say this. It is still, of course, the exact same number. The number doesn't change, right? How I wrote it changed, but it doesn't matter. If we have this number, that is the actual byte pattern, you could say, that it has, right? And so this is it for this episode. In the next episode, we're going to talk about byte ordering and why it matters, when it matters, and kind of why it exists, maybe, and so on. And so we needed to talk a little bit about bytes, right? And next episode is going to be about what about when we have several bytes together and we do actually interpret them. First of all, why does the difference sort of exist here between different byte orderings, how to order these bytes to make up bigger values and so on. 2, how does Odin help us sort of navigate this space? And yeah, we're going to talk about byte ordering in general and take a look at an example of this in practice. So that's it for this episode. I hope it was informative. If you like this content, leave a like on the video, please subscribe. It will help certainly in the future with making these videos and so on. And have a nice day, and ciao.